This video is about my paper titled Weighted K-path and Other Problems in Almost O star 2 to the k deterministic time. In the K-path problem, one is given as input a graph G and an integer k, and the question is simply whether G has a path of length at least k, or equivalently a path of length exactly k. There are quite some variants of this problem. For example, the graph may or may not be directed, and there may or may not be h-weights. However, all these variants can be solved in polynomial time if the graph G does not have cycles, and they are also NP-hard if such a guarantee is not given. The aim for today would be to, so we assume that k is small, and therefore we aim for algorithms with the running time f of k times something polynomial in the graph size, where the function f should be small. That is, we're going to study the fixed parameterized complexity of the problem. Now, it's already a pretty neat observation that there exists an algorithm with such a running time, and actually f of k will be k factorial. And the algorithm is really cute and it fits in this box. So what you do is you repeat the following k factorial times. You pick a random ordering of the vertices that you call v1 to vn. So we are working with the directed version of the problem here, by the way. And then we return true if a particular sub-digraph has a k-path. So that graph is formed by taking only the edges of the type vi, vj, where I is before j in the ordering. And if after all these trials we were not successful, we return false. So by the observation from the previous slide, line 2 actually runs in polynomial time. So this algorithm indeed runs in time roughly k factorial. And it's if you haven't seen this algorithm, maybe it's a nice exercise to convince yourself that indeed this is a Monte Carlo algorithm. That is, if it outputs true, it's always correct. And if there is a k-path, then it detects such a k-path, it outputs true with probability, at least some constant. Now that's a quite clean k factorial algorithm, but if you actually want to go below that, it turns out there has been a lot of studies on this already for many years. So here I summarized quite some results, and what I also summarized is 3 criteria of these algorithms. One, whether the algorithm is randomized or not. So there's a k factorial algorithm from 85, but that's actually deterministic, so it's a bit better than the one we just saw. Some algorithms also can handle these h-weights that I mentioned, and some algorithms can also deal with the directed case. And as you can see, there are quite some fast algorithms. Actually, there's even an algorithm running in time 2 to the k and one that runs in time 1.66 to the k. But both were not deterministic and were not able to deal with the weights. And what we are doing in this result is, in this paper, we present an algorithm that runs in time roughly 2 to the k, and it has all the desired criteria. So one thing to note is that this problem is also interesting when k is equal to n, because then it's a Hamiltonian path problem. And getting faster than this 2 to the k while staying deterministic or extending to the weighted case or the directed case, these are actually all quite interesting open problems. In particular, for the Hamiltonian path, for Hamiltonian cycle problem, so there is a 1.66 to the power n randomized algorithm that only works in the unweighted undirected case. But there is also a 2 to the n time algorithm that works in the directed case, in the weighted case, and is deterministic. And these are actually, in these senses, the best algorithms we have for this problem. Okay, so all these algorithms were not just, the value in these results were not just in getting slightly faster algorithms, but also there has been quite some development in different algorithmic tools while trying to get faster algorithms here. And what I do here is I distinguish 4 main methods, which are the representative set method, the color coding method, and a method based on universal sets. And then the most recent one is the group algebra. And when you look at the more recent results from the last 10 years, you see that actually mostly they've been a mix of this representative sets method and the color coding method. So I'm not going to introduce all these methods in detail, but what we see in the new result is that it's a mix of these first three methods, and I will occasionally point out where there are links or where I built on these previous methods. The group algebra method I'm not going to discuss further. Okay, so let's start it with describing what this paper is doing. So the starting point is a starting point that you could have with the general application of the divide and conquer paradigm. So we have our path, and it's natural to try to partition the path, the solution, into two solutions or partial solutions by considering an edge that's roughly in the middle. So let's call the edge t prime. If you would remove it, of course, the path would break down into subpaths or subsolutions. We could call them P1 and P2. And now the question arises, when do the partial solutions P1 and P2 combine into a global solution? And the point here is that you don't really need to know the structure of P1 and P2. They will always form a solution together unless they are intersecting. So actually you only need to know the set of visited vertices of P1 and of P2, and these, if P1 and P2 they together are compatible, so these two partial solutions form a global solution if and only if these set of visited vertices, if these sets are disjoint. So we only care about the set A of visited vertices by P1 and similarly B. So if you would think of the compatibility matrix of this situation, and the compatibility matrix in general is a matrix where the rows and columns are indexed by partial solutions, and you put a 1 there if the two partial solutions are compatible. In this scenario, it's some kind of disjointness matrix. So if n denotes the number of vertices of the graph, and k is the k from k path, then the disjointness matrix here would be indexed by all subsets of the vertex set of the graph, and then an entry at row A and column B is defined to be 1 if A and B are disjoint, and if the cardinality of the union is equal to k, and it's 0 otherwise. So with this bracket notation here, I mean that we put the 1 if the proposition is true, and we put the 0 there otherwise. Okay, so now we set up some nice matrix. We want to do some linear algebra with it. And to facilitate this, I'm going to define another matrix, which I call the element convolution matrix. It's indexed in the same way as the disjointness matrix, but it's also denoted with an element E, which you could think of as like one vertex of the graph. And it's also a binary matrix, but here the ones of the matrix indicate that the element E is not in A, and if I union A with E together, then I get B. So intuitively you could try to say, like, I want to insert the element E into A, but I can only do this when E is not in A already, and if it's not in A already, then I obtain B by doing this insertion. Okay, now I'm also going to define a family of vectors, and for this definition you should recall the picture we saw on the previous slide. So we have this situation, this partial solution P1 that ends at T, and the vector ATP of A is going to count the number of partial solutions consistent with this fingerprint A. So it will be the number of paths V1 to Vp in the graph G that end at T, and the set of visited vertices is exactly equal to A. So note this also implies that the cardinality of A is equal to P. Okay, now I defined this vector and I defined the element convolution matrix. I can actually show you a recurrence, and the recurrence shows how to compute the entries A, T prime, P, so that's about paths of length P, if you only computed the entries A, T, P minus 1. So only the information about paths of length P minus 1. So what's the idea here? So to form a path of length p that ends at t prime, of course what we can do is we can sum over all possibilities for the penultimate vertex in the path. Let's call that t, so we sum over all possibilities. Then we better have that there is already an edge from t to t prime in the graph, otherwise we can not complete this into a path. But if there is such an edge, then we can count the number of paths with the structure as the number of paths of length p minus 1 that end at t. But then we need to do the element convolution with the element t prime, because the set of vertices, visited vertices now, we need to add t prime to it, and simultaneously we also need to make sure that t prime was not visited yet in this set A. But fortunately the element convolution matrix is doing that for us. Okay, so with this setup we are interested in the vector ATK, which is about paths of length k. In particular we need to sum over all vertices A, actually also over all vertices T, but I didn't want to dwell too much on the details. So this is roughly the number of paths that we're interested in. And we're going to phrase this in terms of this disjointness matrix from the previous slide. So note that this is also equal to this quantity here. So I multiply A with D, and then I look at the entry indexed by the empty set. And this holds because, well, every set is of course disjoint with the empty set. Okay, so recall that this, or remember, this is the entry we would be interested in the end. Okay, so now I introduce these two matrices, and now follows a pretty obvious insight, but somehow that helped me a lot in writing this paper, so I really want to spend a slide on it, which is that these two matrices actually commute. So C times D is equal to D times C transposed. And the proof is, well, if you look at the entry AB in both of these products, they are both 1 if and only if the element E is not in A and also not in B, A and B are disjoint, and the cardinality of the union needs to be equal to k minus 1. So yeah, that's a one-liner, but very useful. So now let's take this recurrence that we have seen before, and recall that I said we are not really necessarily interested in the vector A, but only in A times the disjointness matrix. So what we could do is we could just post multiply here on both sides with the disjointness matrix, which does not really right away give a useful recurrence or so. However, we can use the commutativity property to swap these two around, and what we see now is that if we are interested in the entry A t prime p times d, then we only need to know the information about the entries a t p minus 1 times d. Yeah, so we can it is sufficient to just compute this this image of A with respect to D instead of A completely. And that's of course very useful, especially if this disjointness matrix has low rank. So suppose that it can be factorized in L times R, capital L times capital R, and the common dimension of capital L and capital R is lowercase r, and let's say R is very small, which is an assumption that is bogus actually, because it has high rank, but we'll get back to that. But suppose that this matrix has low rank, well then actually we would have a nice idea. So what we can do is we can compute the vector B TP, which is defined as A TP times L, and we are going to compute this bottom up. So we start with P is 0 and then all the way to K. And this, by the way, connects with this representative sets approach that I mentioned. So I translated these things in linear algebra now, but often this B is called the representative set for A. Yeah, so we work with these representative sets instead of with the entire vector. And if L has only rank R, then the dimension of B is only R. So that's actually, if R is small, that is actually not so much information. Okay, so the idea would be to compute all these representative sets for these vectors, and then in the end you have your vector btk, which would be a representative set for atk. And of atk we knew that we just need to know atk times the disjointness matrix evaluated at the empty set. This then could be computed as btk times r, because btk times r is a times l times r, and l times r was d, so we have this equality here. So this would be a nice approach to actually make things work if this rank R is small. However, there are two issues here that I didn't really talk about yet. So first of all, how do we maintain this representative set? So if you have your representative set for the entries a, t, p minus 1, how do you compute it quickly for these entries a, t prime, p? So there are two things in the recurrence you need to do. So first of all is you need to sum a bunch of guys here by the summation that's written there. But yeah, summation, that is actually very easy. You just can sum the representative sets together, these vectors, as normal coordinate-wise addition. That's completely fine. However, there's also this thing where you do the convolution, and that turns out to be a bit more complicated. So the challenge that we still need to do here is, if we have a representative set of A, so we have a vector B which is equal to A times L, then we need to quickly compute the representative set B prime of the vector A times C N E. So we need to quickly compute this B prime, which would be equal to A times C times L. So that is something that's non-trivial to do here. And of course we would like to do this in time linear in the rank. So that makes it more challenging. But if you would be able to do so, again, because I can reverse things back here, if you would have such a quick routine, then you can actually just plug and play with this recurrence. And if you have this representative set for ATP minus 1 for all t, then you also get the representative set for AT prime p minus 1. And then the whole approach would work. The second issue is that in this approach I'm assuming that the rank, that is R, is at most 2 to the k, but it turns out that this matrix D and K, it actually has a full rank, or no, maybe not full rank, but as large as makes sense. Yeah, and that's way too large. Okay, so two issues, and now I'm going to briefly discuss how we bypass both issues in the paper. So the first one is kind of loops back to the color coding approach. So I'm actually going to, for the sake of this presentation, redefine the problem we are solving. So we're going to, instead of solving k-path, we're going to solve partitioned k-path. And in this problem, one is also given a graph, but also a partition of the vertex set into S classes. And now we are looking for a path that visits exactly S vertices in each of these classes. And we should think of S as square root k. So we have partitioned also the path of k vertices in square root groups of size square root k groups of size square root k each. And efficient reductions from k-path to partitioned k-path exist. For example, if you don't care about randomization or deterministic algorithms, what you could do is you could just take a random partition of the vertex set, and with some decent probability the k-path, the set of k vertices, gets evenly split in these k parts. Okay, but for now we are going to solve the partitioned k-path problem. And it turns out that the disjointness matrix, or the compatibility matrix for this problem, will be a Kronecker product of the original disjointness matrix. I will show that in the next slide, but first, if you do not know what the Kronecker product is, let me define that here. So let A be an n by m matrix and B be an n prime by m prime matrix. Then the Kronecker product of A and B is the n times n prime by m times m prime matrix, which is defined like this. So the rows are indexed by pairs of rows from A and a row from B, similarly with the columns, and an entry is defined as the product of the two relevant entries in A and B. We also consider the S Kronecker power, which is A Kronecker product A in that S times. There are some nice properties of the Kronecker product. It mixes in a natural way with the normal matrix product, as you can see here. And also the rank of a Kronecker power is the rank of the matrix to the power that you took. Okay, so now the promised slide where we relate this. So we had this partitioned k-path problem. So now the k-path, it visits in each of these blocks of the partition a set of vertices, and now we need to know of each of these blocks. We need to know which vertices are visited. So the fingerprint, or you could say, is now more naturally a tuple, an S-tuple of sets. And the two paths are now compatible if and only if they are disjoint in all of these parts separately. So the new compatibility matrix is the Kronecker power of a smaller disjoint matrix. So we have universe U, which is the size of the VI's. But in each block we only have S vertices, so that's why we have an S here in the subscript. Because AI union BI now needs to be of size S. And then we have this Kronecker power there. Yeah, so it's kind of similar to the disjointness matrix we had earlier, because there is this simple reduction with randomization. However, Kronecker powers are easier to deal with computationally. So this is the advantage here. Okay, so now we are finally ready to challenge this, to tackle this challenge 1 with Kronecker powers. It's a bit technical, but I want to show you the formulas here. I don't expect you to understand all of it. So suppose that we still have our factorization, but now it's like the disjointness matrix with smaller parameters, because U is the size of the VI's and S is square root K. Then I'm claiming that if you have this representative set B of A and an element E, then you can compute a representative set B prime of A, where you do the element convolution, and B prime looks like this. So it's a bit of a complicated formula, but what I want to tell here is that only something non-trivial is happening in the ith block, which is the block where the element E resides in. And if you look at this ith block, what we're doing is we're multiplying with R. So then there was already an L, so there's L times R, so now there's times D. Then there is the transpose of the element convolution, and this you may recognize as the right inverse of R. So you're trying to, with this right inverse, you're trying to inverse the multiplication by R earlier. Yeah, so the claim is that this is then a representative set for the vector A, where you do this element convolution. So the element convolution also looks a bit more complicated now, because in the ith block we only do the convolution. Yeah, the proof is some arithmetic. Maybe I want to quickly go over it. So first you just expand the definition of B prime by substituting B with A times L Kronecker power S. Then what you do is you use this mixed product property to take the S into the parentheses here. Then we use the commutativity property of C and D. And now what we see is D is of course equal to L times R. And we see that R times R transposed times R transposed inverse of course cancels, so that becomes an identity matrix. So things become a bit cleaner again. And now we just have this C here. I still have a transpose that I forgot to remove here. Yeah, and if we again rewrite this in cleaner form, we get exactly the expression that we wanted here. Yeah. Okay, so that's a nice way to compute this representative set where we did the element convolution. Actually, you can show again from this research line of color coding with some hashing argument that this U is at most K squared. So if you do this matrix multiplication here, if you do that in a naive way, so the running time would be something like the rank of the whole thing, which is r to the power s, and then the matrix dimensions here, which is k squared. Actually, you choose square root k, but u is k squared. So because we have this property, this is actually still quite innocent. So if you do this in a naive way, then this b prime can be computed in roughly this time as stated here. Yeah, but of course this still assumes that L and R gives you a small rank R. It gives you rank R factorization of the disjointness matrix where R is small. So it should be of size roughly 2 to the s, because then we get here 2 to the s squared, which is 2 to the k. So that's about it for challenge 1. So we tackled it with these Kronecker products. Challenge 2, so that should have been a 2 there. How do we tackle challenge 2? So actually we just use something else, what I call Boolean rank here. Well, it's an established notion, which is also a factorization, but you do this over the Boolean semi-ring. So you don't have addition and multiplication, but you have or and AND. So it turns out that this disjointness matrix can also be written as a big OR of R terms of an AND of two matrices. And here R is roughly what we want, so it's 2 to the s. The factorization is also not so difficult. It uses can for example be done using universal sets. So that's another one of these methods that we also use. That was also used previously for the k-path problem. So that gives the required factorization over this Boolean semi-ring. But maybe things start to be a bit scary here, because in my previous approach at some moment I had this right inverse. So there was some inverse, and of course the property of semi-rings is that we don't have inverses. So what's going on here? And here is actually some non-trivial idea that was also needed in this paper to pull this off, which is some kind of inverse in semi-rings. And actually it turned out that in any additively idempotent semi-ring this idea works. So what we do is we have some ordering. So if we have two vectors x and y, we say that x is before y, denotes that x is at most y in each coordinate, and at most here means, for example, in the Boolean semi-ring, the thing that you think it means. So 0 is at most 1. And now if you want to compute this inverse, so b times an inverse of a matrix, we can define it as the unique maximal vector, so maximal with respect to this ordering, such that x times r is still at most b. So you can think of many vectors with the property that x times the matrix is still at most b, but there's always a unique one that is maximal, but it's still below that. Yeah, sorry, something went wrong with the animation here. And yeah, so that's the kind of inverse that we're using, and that turns out to work. So there are some technical details here. I'm not bothering you with too much. Please have a look in the paper. In the end, it's rather short, but it's quite subtle. Okay, so now I still want to briefly say something about the main tool that we have in the paper, which is of dynamic representative sets. So that's the main technical tool, and from this all the other observations hold. And it's basically what I told you here, and it actually works over any semi-ring S. So we have this factorization of the disjointness matrix in L times R, and there is a quick way to do this element convolution in the way that I told you. But it doesn't work with the Kronecker product. But in the proof there is this reduction to the Kronecker product. And as consequences, the weighted directed k-path problem can be solved in this particular running time, and also some other bunch of problems can be solved quite quickly. Yeah, I sketched some reductions here with previous approaches. I'm running out of time, so let me just show you the last slide here. So the main result was this k-path. The new technique was dynamic representative sets, also has many other applications. The key idea is to really put things in terms of linear algebra, and that these two essential matrices commute, and also this notion of inverse of a matrix that works in any idempotent semirings. There are quite some interesting follow-ups. I just want to put them there for your entertainment.